Okay. Hello, everyone. Thanks for having me here. So today I'm going to talk to you about open clusters and young associations in the neighborhood and the new database that we have been setting up. The mic's not close enough. And how is this? Okay, I'm gonna need to hold it. Yeah, but it was rubbing earlier. I'm gonna try it. Problem is that if it's rubbing. How is that? Okay, I will. Yeah. Thanks, Adam. Oh, it's stuck. Whatever. I'm gonna leave it there. Can you still hear me, everyone? Yeah? Okay, perfect. So I'm gonna tell you about a database we've been building and how you can all use it for all of your open clusters and association needs. So let's start with more technical problems. All right, I'm gonna switch it on the computer. It's gonna be simpler. So I'm gonna talk about why young associations are useful. And okay, let's go back. Oh, I think this thing has a delay.
I think you just need to flip it on the side.
It's on. All right, so I'm gonna tell you about why young associations are useful and some of the new discoveries that have been made using Gaia. And then I'm going to talk a bit about the Mocha database and then some future prospects with upcoming missions. So let's see if what's happening with the clicker is that it's late. So I'm just going to use the computer. So when young stars form, they form in large complexes of molecular clouds. So they form in very large numbers. And you get both loose associations as well as gravitationally bound open clusters in the end. This visualization here is an amazing work by the Starforge collaboration. If you are working at a planetarium like me, you might be interested in that they have a full dome view of this visualization, and it is quite exceptional. Loose associations typically disperse pretty rapidly due to all of the interactions that they face during their galactic orbit, but open clusters last for a while longer. So we can find open clusters that are much older. But both are very interesting to us because they provide a way to age date stars very accurately because we can use a collection of stars born together and then combine many different age dating methods together. So why do we want to know the ages of stars? There are many good reasons why we might want them, but there are two reasons that I am particularly interested in. One of these is to discover and characterize exoplanets at calibrated ages. So this allows us to paint a picture of how exoplanets evolve with time by finding some at many different snapshots in time. But it's also useful to determine the masses of substellar objects. As you know, substellar objects like brown dwarfs and planemos, they cool down as they age. So the only way that we can make predictions under masses when they are isolated in space is to rely on models and to actually know the age. Recently, Gaia has really helped us better understand the solar neighborhood. So it's measured precise parallaxes for 1 billion stars. And here we are seeing a simulation using Gaia Sky of the nearby real positions measured by Gaia. But it's also important because it measured the proper motions for all of these stars too, and also radial velocities for a subset of these stars. So this really gives us a kinematic view of the solar neighborhood to an extent that was never possible before. And this has precipitated a lot of discoveries recently. One of these is a discovery of really large tidal tails with a diameter of 800 parsecs around the Hyades. So you can see these papers for the discovery and further characterization. So this extends to a much larger space, the locations where we can find stars, exoplanets, and brown dwarfs of known ages. And some of these structures are very interesting because sometimes they come closer to the sun and allow us to detect fainter substellar objects and exoplanets. Another example of this is some of the coronae found around open clusters by Maingast. And not all of these are tidal tails. Some of these are too young, and they're probably loose associations that formed from the same molecular cloud complex as the associated open clusters. So there's a lot of these in the solar neighborhood, and we are still finding a lot more. For example, there's a pretty well-known paper by Kunkel and Covey who used a machine learning clustering method called HDB scan to identify a large number of co-moving structures in the galaxy. But there was an empty bubble within around 60 parsecs around the sun. And that is caused by projection effects of similar velocities, but viewed everywhere on the sky. And my PhD student, Leslie Moranta, used a different approach of clustering based on full kinematics, XYZ, UVW, not just projected kinematics. And she discovered a dozen new moving groups by doing this, as well as extensions of known coronae. One of the groups we have discovered appears to be a host for Luhmann 16, so the nearest brown dwarf binary. So this is called the Oceanus moving group, and it has an age that is consistent with the model-derived ages for Luhmann 16 at around 500 to 600 million years. So this is just an example of why finding a very nearby group is exciting, because it allows us to do a lot more with substellar science after that, because it's just nearby. But then we are facing a problem in using all of these new amazing data sets, in that we cannot use spreadsheets anymore for this particular science. I have been a big fan of having my 1000 CSV or Google Sheets, but I ran into a wall recently, a couple of years ago, and I was forced to gradually move towards more and more scalable databases. I started with SQLite, but then moved to a proper SQL database. And I decided to make this accessible to the public in a database that we call the Montreal Open Clusters and Association Database. So yet another acronym that's made on purpose to sound like what I wanted it to sound like. So for those who don't know, I'm a huge coffee geek, and mocha is a coffee variety, so that's why I chose this. And in this database, you can find a lot of open clusters and nearby associations. I'm trying to be complete out to 500 parsecs, but I am not excluding open clusters that are further out necessarily. So I am just not necessarily complete at further distances. However, recently there's a Hunt and Riefert 2023 paper who published a large number of open clusters to much further out distances, and those are all coming into MoCA. So we have also most substellar objects and brown dwarfs, thanks to the work of the Ultra Cool Sheet team. So I wrote some packages to mine the data and add it to MoCA, and you will see why this is useful, not just as a replication of the data set. One example of another database I am mining is the NASA Exoplanet Archive, and this allows you to plot exoplanet properties with ages in the case where they are members of young associations. As you can see, there are not many exoplanets yet with known ages, but there is rapid progress being made. Speaking of which, we are also using the MoCA database to build samples for exoplanet searches. So this is one example of a tentative new hot Jupiter that we found around a 20-million-year-old M dwarf with the NIRPS spectrometer. We are still in the process of confirming it further because it's a very active star, and Gaussian processes sometimes can be tricky. But we trained a Gaussian process here. By we, I mean my student, Leslie Moranta, trained a Gaussian process on a test light curve and then fitted that to our RV curve with a Keplerian solution. And besides the overfitting of the Keplerian solution, we have a Bayesian information criterion that suggests the exoplanet is favored by a wide margin. So we are starting to be gradually convinced by this, but we're still gathering more data. But this would be, to my knowledge, only the second young hot Jupiter object, which could suggest that these objects need to migrate fast because by 20 million years, it didn't have much time to migrate inwards. In the MOCA database, we are also now organizing all of the star-forming regions and associations into a hierarchical structure, which you can also explore on the website. So there are a lot of different ways that open clusters and young associations have been split up in the literature. And so we are gradually building a hierarchical view of these. Also, the database doesn't only contain raw measurements, it also contains a uniform set of calculations that are refreshed every time a new measurement is added. So, for example, if you have many different parallaxes for a given star, it's going to select the best one currently available. If you have 1,000 different radial velocities, it's going to try to figure out the system, the center of mass radial velocity as well as it can in order to compute the UVW velocities. And then it's going to run some Monte Carlo simulations to build average UVW XYZ along with error bars and many other secondary properties. And so we have built a large library of codes that not only mines SIMBAD for all the plausible cross matches between catalogs, but also does further cross matches and then downloads the relevant rows of many catalogs like TUMAS, WISE, Gaia, all of the data releases, and then further mines these catalogs to withdraw the RV, the parallax, and all the useful info, store them in a uniform way in the relevant tables, and then recombine them and repropagate this across the whole database. So it's a pretty complicated schematic, but it's basically illustrating how there are many codes behind the database that are always refreshing so that we can always get the best measurements available. So there's a large number of observables currently stored in the database. This is not an exhaustive list, but as you can see, there's now a lot of kinematic measurements and magnitudes and everything available for every star. And we did a lot of work to document everything properly. Every table and every column of every table has a detailed description on the website with all of the units and how they were derived. And you can also get a view similar to what you get on SIMBAD for a single star or a single association, but it's all uniform. So unlike SIMBAD, you are not going to go through SIMBAD or Vizier where every paper is going to have a different unit, for example, for the RVs, or some of them are going to be statistical RVs that are not actual measurements. Here, everything is uniform, and there are a lot of clickable links that bring you to the summary pages of a given star, or even to the reference. And you also have access to some basic data visualization tools with Python Dash apps that you can run in your browser. For example, here you can interactively choose some open cluster or associations and display them in 3 dimensions and then go around it. You can do that in velocity space also. And we built a Python package to make it easier for you to interact with the database. You can download data from it, but you can also upload a temporary table of your own stars, for example, to cross-match it and download any row you want from MOCA. It would be possible without our package if you are well-versed in some SQL packages in Python, but the wrapper makes it just a bit easier. You can also interact directly with the database using some user interfaces. There are a lot of them that are freely available on the web. This is an example with the SQLace. And you can already access it at mocadb.ca. So keep your eyes open for a big upgrade. Currently, there's a lot of data already in there, but we are preparing a paper that's going to describe the whole database, and along with it, you will see a very big update to the data in the database. Another thing we are using the database for is to refine our models for young associations that we use in Banyan Sigma. For those who have never heard of it, it's a tool that allows you to determine a membership probability in young associations, especially when you don't have a radial velocity or a parallax. It can allow you to marginalize over the missing parameters and still obtain a membership probability. So we have extended this to much further distances. And one of the crucial upgrades that we made is that we are now using the extreme deconvolution package of Joe Bovee to really represent the intrinsic spread of the stars without the error bars and actually take a full account of the error bars and their covariances to really dig into the real internal dispersion of the group. We are also using a combination of many multivariate Gaussians when the shape of the association warrants it. So basically, if the Bayesian information criterion warrants using more than one Gaussian, we do. This is useful, for example, for the Pleiades or some other dense open clusters where the wings are wider than a Gaussian, but also for other more complex distributions like the Hyades tidal tails. So currently, apart from overhauling Banyan Sigma, the biggest utility for us will be to find planimals after that with Banyan Sigma. But then we are going to measure the ages of all the new associations that Leslie has found using test rotation periods. We are also adding galactic orbits with my student Dominique Couture, who is also using that to do traceback ages for these groups. And then our plan is to start searching for even more planimals and age-calibrated exoplanets. So I want to talk a little bit about future prospects now. So we can expect soon we will have even more from Gaia. We will have individual astrometry for every star. So we can start doing Kepler fits to stars to measure their masses directly. And then we can combine this with the memberships in order to get mass measurements for stars for which we also know the age. We can also start to detect astrometric exoplanets and then target the young ones, which will be really good targets for direct imaging. And then there are also the WEAVE and Foremost mission that are currently gathering radial velocities for all those stars in Gaia that are too faint for the spectrometer. So we will get full 6D kinematics down to a G-band magnitude of 21. So this will make it possible to run, for example, clustering analyses on full 6D velocities to, first of all, much further distances, but most importantly, on all the M dwarfs in the neighborhood. So maybe we'll find even more new moving groups. There's also the eRosita mission, which has very recently published a data release that contains a lot of new X-ray measurements. It is much more sensitive than ROSAT. And here I am showing you an example of what a student at Rochester Institute, Attila Varga, did with a query in Mocha using eRosita. So you can see the actual sequence of relative X-ray luminosity as a function of age. So this allowed him to do this without having to dig through the literature for every different open cluster out there. Soon we will also get the Euclid mission, which will get us a very deep near-infrared catalog, as well as slitless spectroscopy for about a third of the sky. And by using the actual footprint of Euclid, if I cross-match this with Mocha and use a credible IMF from Davy's recent paper and make the planimal range as pessimistic as I can, we are still expecting to find hundreds of planimals with spectra in Euclid. So this will be really interesting, and we will not be anymore in a situation where we only have a handful of them to do studies of how their clouds evolve with age, for example. But now it's going to be a new era for planimals where it's going to be population characterization. Another upcoming observatory, as you all know, the Rubin or LSST, is going to allow us to get a much deeper survey than Gaia down to R of 24. This, to me, is also particularly interesting because we will get a lot more brown dwarfs and substellar objects with parallaxes and accurate astrometry. It will also allow to bring gyrochronology to a whole new scale. So you are beginning to see why a database is going to start being really useful because we will get even more flooded with data as the years go. With SphereX, we will get even more low-resolution spectra of planemos for free, quote unquote. We are expecting around 1,200 planemos. So here you can see that for those used to these acronyms, we are starting to really probe regions like SCOSEN for planemos. So this will be extremely interesting. And then there will be the Roman mission, which will not necessarily be all sky, but it's going to be more like pick your own project style. And this will make it possible to combine with the Gaia astrometry of potential new exoplanets and directly image them. And there's going to be many more uses to this. Another great one will be to build the initial mass function of more distant open clusters. And here I am showing the Roman's planned wide area survey, which will cover 5% of the sky, but down to a magnitude of J of 25 with spectra. And we are expecting about 150 planemos from just this wide survey alone. And last but not least, we will also have the NEO Surveyor, which is kind of a successor to the WISE mission, which will allow us to dig much deeper in terms of the cold substellar objects and will allow us to do proper motions. And for those that are also detected in WISE, we'll get a much longer baseline for kinematics. So NEO Surveyor will also detect a lot of potential planemos. One difficulty here will be that we don't get the spectra automatically. So confirming them with spectroscopy will be a challenge. But as you can see, with all these new data sets, I predict that many more of you will start hitting a wall with CSV files and Google Sheets. And you will, I don't think the solution is for everyone to rely on one database, but I think at some point, every research group will have their own databases. And we'll have to find ways to communicate with each other, mine each other's databases. But I think a database approach is going to be required in astronomy. So thank you, and I'm going to take your questions now.
John, may I remind you to say your name and your institute before you speak, if there's a Zoom question?
Brian Curry, Austin. Hi.
Oh, hey.
Great talk, Jonathan.
Thank you.
I was excited to see the noting of hierarchical structure in your
Yeah.
I'm wondering where that comes from. Is that based on just like people in the literature just saying, oh yeah, this is in this, or do you have your own method of assessing that?
Yeah, it's very hard because you can hardly have two different hierarchical structures for one database. So you're actually the person who really forced me into doing this with your recent work. So shout out to you. But actually, oh, and I forgot to repeat the question. So why did I decide to do a hierarchical structure in MoCA? So there were already some known hierarchical structures, especially, for example, in SCOSEN with the embedded open clusters in there. And but yeah, with your recent papers, with all of the spyglass groups that are structured in a hierarchical way, as well as other papers based on HDB scan, which is this clustering method, it is inherently placing everything in a hierarchical structure. Sometimes it doesn't really have physical meaning because it's going to group together some completely distinct star forming regions. but sometimes it is actually warranted and it's a judgment call. So I am referring to both the papers and what they say, for example, in your papers when you say this is a substructure of this, but then I use a lot of 3D visualization to really make sure that the spatial extent makes sense, that there are stars in common. And one thing that you see in the summary page of a single star or a single association on a MoCA, rather on a single association page, you see all of the overlaps in membership. So say you're looking into one of the spyglass groups, it's going to tell you, okay, there are 400 stars in this group that overlap with another group and 200 that overlap with a different group. So I also used these and just turned everything on in 3D and decided, okay, these look like a substructure of these. But this is one of the more manual parts of the database, deciding what's the hierarchical structure.
And the next speaker come down.
Lynn Hillenbrand, so as someone who runs a kind of similar in spirit database on young stars and star forming, totally right on run about hierarchical structure and how to establish it. So I appreciate how difficult and challenging this is.
Yeah. Thank you.
My question is, how do you deal with the issue of blended data, either spectroscopic or like photometric, where one source and there might be someone's AO image, so it's obviously two sources, and then also in the hierarchy of binarity.
Yeah.
Structure. And the reason my thing is like a test database is out there as opposed to the 500,000 sources that are kind of private.
Yeah.
Public version is exactly this.
Yeah.
How to deal with this.
Yeah, so the question was, how do I deal with blended sources, binaries, and companions? It's a very hard problem. So currently, I have not focused most of my efforts on this, but I made the infrastructure in a way that it can accept these. So currently, what I do is when there is resolved spectroscopy for individual components, I make them separate entries in the database. And then I have a table that allows a system to be determined as a companion to, a star as a companion to another star. And those are listed separately in the database. So then they can inherit some properties from each other. But one of the big challenges of this is that Simbad uses an approach where you might have star A and star B, but also a different page for AB in the database. So AB might be matched to one of my stars, but only A is matched to the Gaia entry, for example. So I have some work to do to dig into, because I'm using A and B and making B a companion of A, but I'm not taking separate entries for AB unless it's just a star that doesn't have resolved spectroscopy yet. So there are subtleties like that that are really hard to deal with, but I'm just planning for it to be doable with the database. And as I encounter stars that I realize are companions to other stars, I'm adding them as I encounter this.
Okay, just one time, quick question from Zoom.
Uh-huh.
The Zoom is on. Right.
Okay, so the question is, what's the radial velocity precisions of sources within 500 parsecs in MoCaDB? And there is no single answer to this. It's a compilation from the literature. So it's all over the place. So there are some that are up to about 5 kilometers per second. I'm not using those much with much poorer precision. But they're all in there. Even if you reported an RV with a precision of 20 kilometers per second, it's just not going to be flagged as adopted and included in the calculations. But the real precision of our UVW velocities, the real floor that we have right now for convective stars is about 0.2, 0.3 kilometers per second because of convective blue shift. And it's hard to predict it on a population basis, which star has exactly how much convective blue shift. So the floor of accuracy on UVW is usually 0.2, 0.3 kilometers per second for convective stars. For non-convective ones, it's limited by our knowledge of the precise mass and radius to correct for gravitational redshift. So, but this can be a bit more accurate if you have very accurate masses and radii, but so it's anywhere between 0.1 and 0.4 kilometers per second. Yeah. Thank you.